Dear colleagues, my name is António Viana da Fonseca. I'm professor in the University of Porto, and I'm sharing today with you a record of a lecture that was held and presented in the symposium on cone penetration test CPT22 in Bologna some weeks ago, in fact, in the 10th of June. James K. Mitchell lecture was created by the Technical Committee of Ground Characterization by In situ tests, which I have the honor to be very active, in 2004 for the second International Conference on Site Characterization held in Porto. And we had the luck to have Professor James Mitchell with us. But prior to that, we prepared the launching of this lecture, which is now the 10th that I will deliver, that I did deliver in CPT22, and I'm recording to be available in after our meeting of the TC decision to begin this series of videos to be available to the colleagues. So if you allow me, I will start sharing the presentation, which in fact happens to be also available in our committee website that you can look for anytime. It will be in YouTube. So let me just start the sharing of the PowerPoint. And yes, so the subject of my lecture in Bologna was more like a collection of my experience in the last years, both in the university or consulting, but even more my very recent incoming on the problems that were generated by two main failures of tailing dams in Minas Gerais, the state Minas Gerais in Brazil, and one of them where I was strictly very much involved together with colleagues of UPC that I will refer in a moment. So then the title is this: In situ and lab tests work together, in my view, in most of our colleagues' views, to reduce uncertainties in tailing storage facilities. That's the term that is commonly used, tailing storage facilities, fragility assessment. And I will emphasize this benchmark case history. So again, and to be more or less in line with the previous colleagues, illustrious colleagues, and you can see here, Professor Aisu Yu was the first lecturer, and there are a set of very prestigious colleagues that delivered the lectures in 2 years, except this case here that Fernando Schneider had to deliver it 1 year after the schedule because of the COVID. And some pictures that just remind our colleagues, and Jim playing his sax, which was a tradition, and it is a tradition in our site characterizations conferences, which was held last year in Budapest and will be announced soon in Vancouver in British Columbia, but that will be announced. So if you allow, we can go on and start the subject of my talk. So this is just a general overview of what we can think about these structures. Tailings are granular materials, mostly in most of the case sandy, silty sands, silties mostly. It depends a lot on the quarry, of course, and the processment. But the main thing that we can think about these structures is that they are designed each and every day during the construction. If we are talking about big piles, stack piles, or the traditional tailing dams. And we can do them, as we know, it's not the topic of my talk today to detail the kind of upstream or centerline or downstream construction, which is, it will be a repetition, at least for people that work here in this area. And you can also find any other documents. By the way, I'm writing now finally, or finalizing the written document, which will be published after the permission of the company, Vale, in a journal that will be also announced by in our website in due course. So this is like a diagram, like a schematic diagram of the complexity of these structures. The materials are dynamic mining and processing. They happen to be necessarily variable during all the years that these dams going up in each phase, in each height, with different quarries, or even being the same mine, the variation exists. But I mean, will not be the mainstream of the problem. The problem is all these materials after processing, and I will talk about iron mines. So the core is iron, and we will talk about specifically one case where the percentage of iron is still very high. So heavy material, heavy silt and sand materials, and always launched in during the years with spigoting from the crest to the upstream reservoir, with no more than a general overview that you can look and criticize and analyze in due course. I will go on with our talk. So why do we have these concerns? Because it is recurrent, unfortunately, that we have accidents in these complex structures due to several reasons, and I will immediately discuss them. You can see here 1998 in Spain, Mount Pauli, very, very recent, 2014. Then after 1 year, Fundão, the first big accident in Minas Gerais, a catastrophic disaster in terms of environmental. We do remember that the satellites observed the incoming in the ocean, the Atlantic, of the mud after running for 200 kilometers or so. Then we had also a very well studied and detailed analysis in Cadia, New South Wales, in Australia, 2018, very much analyzed and thoroughly analyzed by our colleague Mike Jeffries in his report, which is public. And finally, we will talk about the last one in Brazil, close to a village called Brumadinho, that I will present some lines in a moment, some illustrations. Well, these materials are common material. Indeed, they are granular, fine, silty, mostly, silty sand, but they have no plasticity, as most of them, the people that work in these areas know, even with our other ores, like gold or whatever. But the practice has been revealing this very high number of failures, mainly in upstream dams. And this is the description that I leave to you read in the PowerPoint, the PPS, that also be available before even the written lecture. And this is the number of failures that have been reported in several sites, which I will not be reading. So we have susceptibility of drop down of the strengths because these materials are highly but strongly brittle. And we will discuss a little bit about this brittleness. It's a long way known subject, and you can see here some results from Castro working in the States with Terzago, Casa Grande. And you can see here that these are the very, very classical results from his thesis. But then I put here some schematic picture of how they stand, how they work when they are loaded by any stress pass that I will discuss also. And by some reason, they get into a very peak, a very high strength and drop suddenly, even before getting into the frictional critical state approach. I mean, the friction angle, which we know very well from the soil mechanics, the critical state soil mechanics approach. But this is strange. This can be considered to be strange, and it is not, it's unusual that these soils happen to go into a very stiff behavior and get it a complex, I think, very fair and high peak strength, but then start immediately to soften and deeply to a residual value. People don't like residual, but in fact it's like a ultimate lower condition. And sometimes, and very often, and now very clearly, this is associated with a process of liquefaction, and it is indeed. But look, the peak is very high, so the undrained peak strength is really very high when compared with this liquefied or residual strength that would fundamentally go towards the critical state line in a process that can be very rapid, very, very rapid. And since we have a non-Newtonian process, which is mud coming into a condition of non-Newtonian laws, it maybe drop down to zero, but just because there is no control even in the lab tests of the stress state. So this is what I described. It is particular that the fact that these materials usually have this behavior when they are loose and they are very contractive, but necessarily is not sufficient. The fact that the materials are contractive, like clays, for instance, and we know that there is increasing pore pressure in undrained conditions, they do not have this kind of behavior, except those sensitive clays by different reasons. But this is a granular soil, and in loose condition should go straight to the critical state line and stay there, or, I mean, in terms of frictionally increase in the friction critical state line. So the key issues is that triaxial undrained compression tests can contribute to evaluate these strengths, these issues, the stiffness associated to a brittle condition. So the materials seem to go with very low increase of pore pressure in the first phase of the loading, which is fast enough to be undrained, and then drop down. So maybe stiffness, high stiffness in relation to the strengths will be an issue, and it is an issue. So we need now to state very clearly that we do not have in the common modeling approaches an easy treatment of this process, because we need, this is not a conventional phase transformation locus, because there is no hardening, after the incoming of the pore pressure increase. And so we don't have the classical plasticity theories available here. So we have to have new flow rules. And there are some models already with this that I can discuss later on. This is very variable. It depends a lot because of that interlocking between the particles that happen to be like high stiffness or high relative stiffness due to the strength. Fabric is an issue. So the fabric that is settled during the process of deposition of these materials is important. And when we do these tests in the lab or interpret even in situ tests, we have to have that in mind. I will discuss also that. So residual shear strength is quite complex if we don't have these very thoroughly tests. And even in these thoroughly tests, in triaxial tests, or even in hollow cylinder, more complicated, difficult in simple shear tests. I will not discuss this. It's too much things to discuss, but I will focus only in some, but it's difficult. So we will have also necessity to go on with studying how to do that easily, at least commonly, by in situ tests, by new approaches. So I have already discussed the fundamental characteristic of this residual or post-peak shear strengths that should come into the critical state line. And what is necessary to have this condition and induce failure of these huge structures? The susceptibility is there, but we have to have hazard. And the hazard, the triggering factors are here, enumerated, but not all, but the main that we could read here, but you will have time to. And you can see that some of the biggest failure case, or at least the most detailing back analysis, etc., analysis in finite element codes, modeling, etc., are here enumerated, described, and you can see that they are quite different. The mechanism, overtopping, immersed root. Very recently, there was a very interesting article from the colleagues from Barcelona that I will talk in a moment about the approach that they model in chasm model that I will also discuss very briefly. And they tend to explain this. Fundão, which was also analyzed by Professor Morgenstern and his colleagues, also by numerical analysis, mostly an overloading problem, which was rapid in raising, although there is some discussion on the relief of the stresses by erosion. The loss of support, which is a problem on foundation. So dikes move, you know, dikes, the wall of the dam, for some reason are settling and rapidly settling, which is enough to create a process of increase of pore pressure into the reservoir and liquefy these materials in very low strengths, residual strengths, and tend to collapse, flow into the crest. El Cobre, dynamic, earthquake induced pore pressure increasing and then the collapse. And finally, Stava seems to be more or less in terms of the dam, a similar condition that we realized in the last panel of Brumadinho. We will see. Here you can see some draws and schemes on the typical stress paths that you could expect in such a triggering process. I will not detail that, but you can see here that drain unloading can be also a problem. I mean, you are relieving the lateral stress of confinement stress, and things tend to come slowly into a specific point, which is the stability locus somewhere in the stress state space. And then at that moment, it starts to fall down rapidly. So in a undrained condition towards residual. And that's a fact. We can do that in the lab, and we can then try to reproduce in the structures. The undrained shearing is the classical, you are putting overload very rapidly in the deposition of these tailings, and for some reason, there is no draining system enough and competent to alleviate, to decrease this natural increase of the pore pressure, accumulates towards again, it could be going to the critical state line, but it gets a condition that drops again down to very low residual values. And then, of course, if you have earthquake or explosions or a vibration in such loose and brittle materials, this comes to the mainstream, the main condition of failing by monotonic after rapid. So it is the same concept, although different stress passes and emulations. Finally, the pore pressure increase, which I will detail in a moment, somewhere inside the reservoir, by some reason, by what we call an unknown factor. We can now enumerate several, but there is always something that can happen that can generate one of these stress passes. And here you can see a general overview, and this I dragged on from this website on the Fondão in 2015 and the report of 2016 where this is illustrated. Anyway, so Dam 1 in Brumadinho. Brumadinho is the village that was mostly affected by this collapse. The mine is called Córrego de Feijão, meaning the small river of bean. That's the name, very simple. So is the small river, little river of the bean, Feijão. Because there are several rivers in these valleys, and that's why water is always very high in the reservoir also. And the draining systems have to be very thoroughly implemented. Well, this is a scheme of the dam, and then I will show you in a moment how fast this happened, as a lot of people know and others may not. So in 25 January 2019, in 20 seconds, the dam collapsed. I could show you a movie. You can go to the web, I think, to internet, and there's a lot of illustrations of that, because there were cameras filming at the moment, observation, instrumentation, and it is terrible. But look, the fractures started somewhere here when they are detailed analyzed. And then you can see that at 12, 18, 23, something was already movement here, and cracks are starting here. Well, 10 seconds after, and there are lots of images during the process, the dam was out. The wall is here still standing, but the rest, this is clearly the sign of the surface, quite vertical, and eventually planar. And you can see the huge amount of mud going to the, unfortunately, the headquarters and part of the infrastructures of Vale, and also running to the population and the village. So it's terrible. It's seconds. And there is no sign, there is no real sign that was thoroughly analyzed, if you, the piezometers, or even the observations, the radar, there are papers on these satellite measurements, etc. I mean, it's really too fast, even for common or even some upgraded recent instrumentation can detect. So we have to be very careful when designing and analyzing these conditions. So you can see here in the top of the reservoir. So this is the crest somewhere here. You can see the valley there, and this is the top of the reservoir, which is something like 1.5 million cubic meters of iron core tailings, very heavy. You can have unit volume like 30 something kilonewtons per cubic meter, and specific gravity around 5 something. Anyway, so you can see the damage, you can see the disasters, the catastrophe, and in the end, the cave, post-mortem area. So we have susceptibility, we do. We have hazard, we may have. We can see that we have to go after this, and we did. We are the panels that work in this analysis. Very, very competent panels, mostly and more detailed two, one led by Professor Peter Robertson, which I consider a good friend, and they did a very good work with the elements that they had at the time, and in the end, with a very thorough analysis of the in situ data and the lab tests that they could have, and then all the lab tests that they could do with a sampling that was limited by the conditions, they got into some conclusions that could be, but afterwards we were challenged to do a reassessment of these conditions with more data, and mainly, as I will tell you, with a lot more lab tests recoiled, with samples recoiled really inside the mass that was that collapsed. I will explain in a moment. So this is the section of the failure zone. It is almost that what was back analysis by the movies and the imaging analysis, which is now very, very competent and very, very, I would say, precise, rigorous. And then after all the numerical analysis that were developed in Barcelona, in UPC, Polytechnical University of Catalonia, with the colleagues António Viana and Marcos Arroyo, that I have to acknowledge for being together with them in this analysis. And in Porto, we did a lot of characterization that I will show you in a moment. The thing is that this is obviously already a back analysis of the old data that could be recovered from the previous in situ tests and some sampling, not undisturbed, but could help in the definitions of all these sections. And this is one of the sections, the section, in fact, that we realized afterwards that was intercepting the point or the area where the increase of pore pressure was generated. And you can see here the shape, which fits well with the imaging numerical deduced and the numerical analysis. But then I had one point to discuss and to show you. There was a lot of concern about these and other dams before the failure, mostly because after the Fundão failure, there was very strict regulation about the conditions of these dams. And they were, I mean, Vale and his consultants were looking for the stability conditions of the B1. And you can see here some of the results of the most, I would say, the latest analysis that were developed in very, very simple, between common, limit equilibrium analysis with the classical circular failure surfaces, and getting the data from the tests that were available. And you can see here with no more comments than the imaging and the values that are expressed in these reports that are public. And you can see here that we could have like 1.09 factor of safety in the red surface in Spencer method. And then I just put here the numerical analysis that were in the final. I mean, a lot of numerical analysis were done during this month here of analysis in CMINI plus FILP. And you can see that it is not really very far from. In fact, it's wider here, is mostly planar here, not circular. But anyway, the problem was there. And eventually a limited equilibrium analysis, if taken with other inputs, could be and should eventually be a very good sign that the dam was at the limit, even in a deterministic approach. And I just want to share you, because it's important for the discussion that we will do, that the laboratory tests, the in situ tests that were interpreted during time and until that moment were a little bit tricky, because there were vein tests in these materials, which are typically silty sand materials. They are not reliable, as we know, because you can have partial draining conditions. And the values that you can see here, which I will not detail, are typically very much higher than the ones that you could get from the reinterpretation of the CPT tests, CPT-U tests that were made on that time prior to the failure. And even the lab tests, which were also considered as a possibility to get the undrained shear strengths and other parameters, but mostly for the limiting equilibrium analysis, were also revealing very high values. And then we realized, not only for this dam, but others, that most of these lab tests were done on dilatant conditions, which means the few undisturbed samples were already compressed during the process, or even the reproduction of the conditions were always on the dry side of the critical state line. So we had tests that could not be reliable, and they were not. So just here, and also on stark correlation, and you can see how different the values come to be in a specific analysis of the CPT-U tests. So critical state soil mechanics is a fundamental approach to get the value, the peak and the post-peak residual or liquefied resistance. There is some confusion in concepts, like post-peak sensitivity in clays is not the same, because these are full liquefaction in non-plastic granular soils, and they can be due to cyclic actions, while when you have this kind of monotonic process stress paths, you may have different situations, I mean, backgrounds on these behaviors. So in this case, there is a steady rising of the pore pressure ratio, and the complete loss of contact between particles can happen in terms of when you are dealing with earthquake, with vibrations. And in fact, in that condition, the full liquefaction can happen, because the particles will not stand together, while in a monotonic process, in a flow process, the particles are provisionally, temporarily in a mud condition, but then they tend to grab together again in a very low level on the critical state line, but still get into the frictional behavior, but then effective stress is very low. So with this in mind, which I describe here in this red box, with this in mind, we have to do specific analysis. And the specific analysis, fortunately, in effective stress state, meaning finite element codes, finite difference codes, finite differences like FLAC, etc., they have to be done ideally in effective stress state fully coupled analysis if the models that we integrate are competent to do that. And there are models already very much competent. Not completely. I will discuss anisotropy in the end of this presentation, but this in fact is available, and we should, and we are going towards this direction more and more, fortunately. And then we can also rely on the limit equilibrium analysis if we have a good interpretation of the limit values, in the end, the very low limit values to be considered. So this is here described. This has been done already in Fundão using North sand from Bean and Jeffries, you know, the model. Even in Fundão, Professor Morgensen and these colleagues did the same in FLAC, both in FLAC. Professor Peter Robertson in the B1 did the same with North sand. Unfortunately, North sand could not be taken towards the end, so they had to use a simplest model, which was a pity. And finally, in recent days, Cadia also, Jeffries in 2019, after the failure in 2018, applied North sand with no problem and illustrated very well. And very recently, some few days ago, I would say, Dan Schottel, Mike, and Miranelli from Napoli, which I know very well, they did this excellent work of back analysis of Tar Island failure, again with North sand. And then finally, in this last panel, which is available again, I emphasize that it's interesting to go there and to see all the details. The colleagues from Barcelona, António Viana and Marcos Arroyo, and the huge amount of people of the team that they had to work with them. They did the reinterpretation of this B1 by using the CASM, critical state for sands and clays, or clay and sands critical states, soil mechanics. Well, I will not describe the model, but anyway, it is already emulating very well the process, although with few limitations that we will discuss. So what do we expect if we have a progressive failure? Rapid failure? Well, we do need to look for the tests that we could do in representative samples in the lab. And I just put here in advance some of the tests that we did. And look at this. This is another material. It's not the material in Brumadinho, but it's similar, very similar. And you can see here that's just to start, that if we do a K0, I mean an anisotropic consolidated test in undrained conditions, if you go in compression, I will show in a minute. But if you go in extension, we have a very, very, very low values mobilized of undrained shear strength. I will be back to this because it is important to realize that in these kind of failures, as in slopes or whatever you can imagine, or even foundations, you may have the need to look for the anisotropy, the induced, the inherent, of course, if there is inherent anisotropy, and induced anisotropy if you have extension tests like lateral compression conditions. And this is very, very critical. You can see that the drain tests were confirming mostly the same friction angle, no inherent anisotropy, but then you have the induced anisotropy, which is very, very, very high. So it's like an alert, an alarm. You mean we have to be aware that the stress passes are not exclusively in compression. So if you go into numerical analysis, you can cope this, but if the model is able to reproduce these conditions, we will see in a moment. And we are looking for the implementation of these anisotropic models in order to reproduce these conditions. Do we need undisturbed samples? We should, but at that time, there were no undisturbed samples in the huge amount of data that was available in the lab, as I told you before. There was no gel push samplers, which in fact is a very excellent sampling technique developed by Kizan company in Japan, and that we happen to work with in a very recent European project, Liquefact, together with Trevi, and with the intersection of Professor Mike Jamelkovsky, and in collaboration with Technoin, Trevi, Technoin, and finally associated with the University of Napoli, Federico II. So we have some experience. It's really a very nice equipment, and we did very, very, very good sampling in sands and silty sands, alluvial, close to Lisbon, as the Italian did in the north of Italy, because they were studying the consequences of the liquefaction of Emilia-Romagna in 2012. So, but we have alternatives, and Vale, for instance, is now working a lot in implementing these systems as a possibility to have good samples to get into the lab, to preserve at least most of the fabric that is inherent to these materials, and to do more representative tests when they want to look for the behavior in triaxials or whatever. Dames and Moore is a very good alternative, as we also realized from the studies that we did in Liquefact project from the European project financed by the Commission. Anyway, but if you don't have, what can we do? We know that mostly of us that work in this area, we know that we can, at least for the critical states, at least, but more than that, if we go towards a reproduction, let's say, try to reproduce the conditions in situ of the deposition very loose, then we can start with the materials in a very loose condition by using the technique of moist stamping. I will not describe. It is well described in different papers, and I just name it here one, and you can see the illustration of the process. And even the triaxial tests are now for the purpose of getting a very good critical state approach, or even to have the latency parameters that we need for a model. Then you can do better if you have lubricated ends like bases and tops, if you have guided tops, if you have frozen techniques to determine very, very accurately the void ratio, etc. It's not an issue. It's just a remark that you can do that, and it is available. So there are, of course, people that say, oh, even that you are putting a different fabric from whatever, and you can even induce a fabric that is not reality because these materials are deposited in slurry, they are deposited in water, pumped. Then my decision, our decision, and I think other people like people from the UWA, David Ray, etc., is that if we do that with a very gentle, almost a null tamping energy, then you can get it very loose. And that's what I call it very light spoon deposition. So this is a kind of moist tamping with no tamping, but just homogenizing in 9 layers or whatever, which is really very thoroughly in order to be very homogeneous, and then you have very high void ratios if you have the technique, like 1.3 or 1.35 or 35, like we got in these materials coming from B1. And there is mostly no fabric. When you then percolate with CO2 and water, the air water, there is an accumulation, and in the end you get lower values like 1.1, 1.15, but the material rules itself during this flow of CO2 and then water. We were very confident with the results. Not perfect. We have no undisturbed samples, but we have some. Well, this is just some of the results that I will show in a moment, and mostly a point that I want to introduce here. We had some small block samples that we compared, and you can see here some comparisons between critical states in undisturbed and remolded conditions, and they fit together. Even in this very, very sensitive representation with this void ratio against the median effective stress for the critical state, the lines that you are seeing there, the black, the brown, and the red are the ones that were obtained by the remolded conditions. And then the other points are undisturbed samples, which are always very anisotropic. And still, the main matrix, when we are standing in the more blackish areas that I will show you, or brownish or red, which means that they are different percentage of irons due to time of the process in the mine, and also due to the injection process. Fines far away, less fines, coarser, blackish because of they have more iron. But then you can see that this is detailed also in the report, and it will be in papers soon. We are quite confident that we could work with these critical state lines. This is described a little bit on this paper that we published some months ago. So the dam is here. The dam failed like that. No details, no need. The system response considerations of B1 was very, very much detailed, and a lot of work on the in situ data. And this system response were based mostly on the tests that were done before, but also looking at 3 experimental sites where we grabbed these new materials, new in terms of characterization, and they were well allocated inside the reservoir, and we managed to get them, by topographic approach, somewhere inside the failure area, around the failure area, and in the bottom of the failure line, I would say band. Wow, how can you do that? And then we got also some material here, which we wanted also to test because they are more clearly finer and with some slimes around. How can you do that? It was failed already. Indeed it was. So you can see here that from the CPTU, from the in situ tests, and there were some good CPTU tests, mostly 1 year before and 2 years before, they were worried about that. We managed to look at where can we get this material, where can we get that material. This is the area of the failure in 2 sections that I will show in a moment. And then, since I knew already that And then we started this analysis by request of the Federal Minister of Public Brazil, together with Vale, because they have all these agreements to know about the reasons. There was a completely open attitude of Vale to look for the possibilities. And then we were there before Christmas 2019, and we decided to what? To get into the mud? No, we had the luck to realize, I didn't know that before, and because I had the images, etc. And then we were there, that there was huge, I mean, I'm always with this because everything is very big. Blocks, massive blocks, that after the collapse and the running of the flow, some of the masses, integer, preserved masses, stood in the borders. And you can see here the this is a draw of the dam. Look, the dam is still here. The dam is still here. And the dam was more or less like that in the crest. And this is the lower part. So we looked at, there are blocks that in time, during 1 year, they just slide down. But the mass was preserved. These mostly here, which was very interesting for us. So we had to go there, and we went there to get the materials, digging into small ditches, enough to go into the interior, the undisturbed materials, and to recoil some few block samples. It's not really, and we didn't have too much time because we didn't have to have all the analysis, but also remolded materials from the interior. I mean, we just carved and we got all these big bags of materials that were transported to Porto, where we did the lab tests. So I should emphasize this in order that we could do more like inside analysis of the materials, which unfortunately was not done in the first panel from the group of experts led by Professor Peter Robertson. They could not get these materials when they went there because they were still very unstable and full of instability, still very wet, and in a moment that it was really impossible to go down. We had the luck to go. So you can see here some images that are in that paper in Soils and Rocks journal. And you can see here the images of these works that we did there. The 3 sites, site 1, site 3, site 3. The site 2 is somewhere here. Look at the mouse somewhere here, long away, because it's a zone where we have more like fines and slimes. And these were the basis of our studies. So you can see that the blocks, what were recoiled like here illustrated, and we are working here sampling the undisturbed conditions. This was really a tough process. But the big bags were the ones that assembled the materials as a whole. And we did identify very distinct materials. The blackish, large zones of these blocks were really blackish with a very high percentage of iron, like 80% or a little less, but huge amount of iron, for all times when the process was not so efficient. And also some more brownish, typically more let's say processed, finer and lighter. And then when you get into the very fine materials, you get into the reddish materials, very much oxidized, older ones, which is on the bottom of the dam. So we did recognize 3 kind of clusters of materials. And then we have here them inside the whole set of samples that were available at that time from previous analysis. So this is our materials. I mean, this is just the region closer to the failure zone after the analysis of this old data. And then when we got there to these sites, we defined with all the materials that we had. This is only the average of each kind of cluster, black, red, and brownish, that we had from every bag, every sample, every undisturbed sample was, of course, analyzed in particle size distribution and no limits. There was no plasticity in any of them, only in the slimes. And you can see here the difference in GS, specific gravity of the grains. You can see like 5, like 4.5, and like 3.85, completely different. The grain size distribution seems very close. Indeed, it is, although you get into the sands and the silts, there is some differences between the very fine and less fine, but mostly the difference comes towards the GS immediately. And then we did all this microscopy and analysis, you know, SAMs, etc., and they are really very different. So 3 clusters for our analysis, for the numerical approaches. And you can see here some of these undisturbed. And the result of that, which is really very nice, and this is already assembling into the triaxial cells where it is always possible, mostly of them, with Bender elements in order to evaluate the VS value. That is very important to define the stiffness of these materials. So let's go on. We are very late. We have to go. And you can see here that we are getting the materials. And you can see here that immediately after we were there, we started to test them in oedometer, trying to get the compressibility, and of course, parallelly in triaxial test to get the critical state line, etc. And in the end, just show you some of the results, which is very clear that the black is much higher in terms of the void ratio. It tends to be compressible less than the others, less fines, more roughness in the particles because they are mostly dominated by the iron particles. And well, in between the red and the brown, there is small difference, which were revealed in compressibility, in weathermeters, and isotropic consolidations, but also in the critical state lines, which is not the only issue that we should be concerned on. We are going towards the main concern, which is the undrained behavior in a moment. So we have that. And just for you to have an idea, if you go to a site that is shallower to a deeper in the same material, because it was the deposition in like a non-linear from the margins to the center, the deeper one in the blocks, you get it a little bit down when compared with the same kind of material upper, which means that it has evolved. It has evolved. Evolved. Yes, I'm repeating. It seems the same material, but the same material is a little bit denser. Well, of course, it had a lot of pressure on it. And it will have consequence even in the particle morphology, which will have consequences in the critical state lines. Then we have all these deformability modulus in virgin or unroll reload, which is necessary for the model. Just for curiosity, the critical state lines, this is detailed in the report and also in that paper. You can see here that we have always a first phase of virgin test with the virgin materials recoiled there, and we get some trend in the critical state line, which in fact, afterwards, after doing all the analysis always with virgin soil, then we had all this material already with higher stress. We put them apart, even the dilatant conditions, we put them apart after testing, and then we start doing again the analysis with these materials, and we realize that the critical state line dropped down. Something was happening in the at the particle level that could explain that. And that, in fact, what we did. And we are still waiting for new analysis. The SEM allowed us to see that the particles that were more rough in the starting of the test tend to evolve to smoother. They tend to lose their roughness. And that was a key factor for what happened after stress. The materials could have a drop down of the critical state line. So this is also an alert. You should be aware of that when you are doing analysis in materials, the same materials coming from the shallower zones to the deeper zones. And this was incredible, like say, reproduced in the 3 clusters of materials: the red, the brown, and the black material. All them has this evolved condition after being stressed up to higher confinement effective stress. So these are lab tests. These are results that were very important to define these critical state and the latency parameters that were then explored in numerical analysis. Just a small remark on the morphology. I will not spend too much time. This is also available in the PowerPoint and here, and you can see that in the written part. But this is just a call back up, drag up of the analysis that we can do in morphology to look for the quantitative indexes that can help us to define the quality of the material and expect different compressibility and critical state lines, which in fact is associated with compressibility, as we know. Convexity, circularity, sphericity, roundness, and roughness is a subject that is now well dealt. We have to be aware of that. We have been doing this in sands. Other people have been doing this comparing different materials like Schuanol in terms of these different indexes, and this can reveal, as in this case, in this very nice Acta Geotechnica work of these colleagues from Iran, they compare sands with mostly similar index except roundness, and that is the gold gohar iron ore tailing, which has a lower value of the roundness, and this has consequences in the critical state line. Even Andy Furia and his colleagues, no, sorry, Barry Lehane colleagues in the UWA, when they realized this in the cone resistance, when they compare sands and tailings, they also realized that you can have completely different resistance, cone resistance, due to this kind of roughness and roundness. But this work from the colleagues from Iran is really interesting because they analyze this brittleness index, which I will introduce in a moment, but is here. And they try to associate them with the end-range shear strength ratio in terms of effective vertical stress. And they realized that these Golgohar tailings happen to have a very higher ratio, strength ratio, having this IB quite incipient, while the other materials that they were studying, like this clean Firucus sand or whatever, they were much more affected by this brittleness, and the consequence was that the strength ratio, end-range strength ratio in peak initial, they call it initial, the one that is in the maximum one, and in residual, which they call liquefied, are highly sensitive to this brittleness. And these materials are more stable for that purpose, while if you look at the surface texture like roughness, as we did, it's the opposite. High roughness comes to be very, very brittle. So this is images of the undisturbed against tests. I'm just trying here to emphasize that we did check the representativeness of these materials towards these conditions. And here I start showing you some of the amazing things that we discovered. We had to look for what kind of consolidation do we have in the lab in order to reproduce the conditions when you stress that in undrained passes, or even in flowing pore pressure, increasing pore pressure, or others like extinction tests, etc. Should we do that by isotropic consolidation of these samples, remolded or intact? And we studied that. And finally, we realized that in terms of instability, at least in these materials, it seems that there is mostly a unique instability line, which is not always like that, but in this case of these iron soils, it seems to be not very, very much different. Although the stress pass is completely different. So if you look for limited equilibrium analysis, you may have a problem, because if you start from K naught equal to 0.5 or 0.7 or 0.1, the stress pass evolves with a very much clearly different energy evolution. I mean, you are plastifying more or less the material in the stress pass when it gets longer or shorter. So I will also show you some of the results if you analyze this in terms of the ratio between the peak shear strength and the effective vertical stress in the field in K naught equal to 0.5 or 0.7 or 1.0, which is not the same. And eventually is not representative, 1.0. It is not. Well, we had to look at the fabric, and we had to look at the variation of this VS. VS is the velocity, shear wave velocity. And this is very important for us to look for if these materials are cemented, hypothetically, or if they are interlocked, they have a very strong fabric, or if they don't have such, or more or less, it's incipient, the fabric, they behave like recent materials. So VS is very clear on that. And we looked at that and we realized that all these tests are consolidation effective, I mean, isotropic consolidation in step by step, and in each step after the consolidation, after the stabilization, which is rapid, but still we wait. Then we do all the tests that we want to do at each and every of these increase of the confinement effective stress. And the VS values have this trend here. I will not discuss the numbers, but these numbers are clearly already very much analyzed by several authors. Carlos Santamarina did that a long time ago. And you can see that materials that have very high B exponents and low alpha, alpha is the constant, and the beta is the exponent, which is affecting the stress state, confinement effective stress. And these materials are typically materials with no cementation, no really evidence of cementation at all, and fabric is also quite smooth. Well, okay, but you are doing that in particles that were remolded. Well, okay, fantastic. But shall they evolve in terms of fabric if you prepare them? Seems not. There's no fabric, or at least evident, and no cementation. No cementation. But you are not showing this in undisturbed samples. We will see that in a moment. So these are the kind of things that we should be working with in the lab in order to evaluate the condition of the fabric, structure, or cementation. Just for you to have an idea, I have here one of the comparisons between the intact, one of these samples, with a consolidation in the K naught equal to 0.5, which in fact it was the compromise that we decided could be inside the reservoir. And we did some steady state analysis during all the years, reproducing the construction of the dam, which is always discussable, but still you do that step by step, and the effective stress that we managed to have in this long-stand increase of the dam can give us an idea of the at-rest stress and repose in conditions of repose. And K naught equal to 0.5 is a very good compromise, but it's not the same in every mass, but that's another subject. So you have here the values, and here you can see that is some fabric. Indeed, you see the A value is higher, the N value is smaller. There is fabric, but there is no cementation, because really there are still values that stand close to the area that were previously shown, that was somewhere here, somewhere here. Fabric, maybe. Cementation, not so much, or null. Anyway, so again, the plotting of these tests. This is another test on undisturbed samples. And you can see here that we do not have so much of that in the lab, even in block samples. But if you go to the in situ tests, and I may say that I'm a fan of in situ tests, my work in the long-standing career and in the committee is mostly also lab and in situ tests. And if you do analyze the seismic dilatometer tests that were performed prior to the failure, very precious data. In fact, they did not the dilatometer tests. The purpose of doing these tests was only to have the shear wave velocity in depth, because the modulus that our good friend Diego Marchetti, son of the late Professor Silvano, which was a very good friend, do remind him with a very care. And well, Diego did a very good work recently, and the modulus of dynamic is very good. So they did that. For some reason, someone called for that, and we had a lot of SDS values, G naught, so VS, and then G naught in depth. And they are all plotted here. All these blue things that you can see here in depth with P prime, or here by this plotting. And you can see that the ratio, I mean, the relation between the VS values and the P prime, again, typical of very low fabric, no cementation. Wow. So you confirmed in the lab with the service samples that you in the field with the VS measurements, you don't have cementation, you don't have. And the fabric is quite smooth. So that gave us some confidence that even doing a good set of analysis based on remolded conditions of integer soils. The whole frame of the particle size is there. Even the particles and the roughness, etc., could be reliable. So lab tests were validated by the in situ information. And you can see here the plotting of all our data from the block samples with the VS coming from the SDMT, and this is quite confident. We are now very, very much happy that we can proceed, and we did. So again, some details on the interpretation of the non-cementation of this. And I will go on because this is in the panel, is the work that was very intense from Marcos. Marcos did a lot in this analysis together with our, we had two teams working together, you know. This side here more experimental, there more numerical, but even in the Plaxis we did some things together. So shear wave velocities and P wave velocities are very good for what? Well, we saw at the moment, at least, that we can have all this information about the reality of the soil as cementation or whatever, but also because we need the G naught. I will tell you why, because it's part of the brittleness, is part of the index that is decisive in the behavior of the materials, being more unstable or less unstable. But also, if you can have the P waves in the lab to check for, if you are saturating well your materials, there is a lot to do to convince people that, look, if you have Bender elements, look at the P waves, and in the P waves, you will have definitely the confidence that you are in full saturation conditions, because it is tricky to go with the B from Skempton, because while B from Skempton, if you don't have P waves, then you have to be very, very, very strict, only 0.98 or 0.99. And that's it. That's our experience when we compare with P waves. By the way, P waves are very important in field in order to know if your water that is being detected by boreholes or even in CPTU is a full saturation, let's say, water level, or it is a standing water level that can be, well, giving pore pressures, but still with bubbles inside, so partial saturation. Not unsaturated, but partially saturated. Anyway, this is another subject that is ongoing in our community. So this is the failure zone. This is the analysis that we could have from the CPTU tests that were available and were analyzed during term. You can see here some of their profiles. And finally, I would be faster in this part of the lecture, because this is the data that we had from intermediate, coarse and fine materials, but then we have to zone this. The colleagues in UPC, CIMNE, had to do a zonation of the zone in terms of the finite element codes. And this is not my mainstream of the lecture, but I will have to tell you that this is described in the panel report, but also in some conference that Marcos did some time ago, and they are already also recorded. And you can see here that to get this like block-ring clustering of the areas, and you cannot do it by small areas, you have to have clusters, and we decided to do like these small rectangulars on the mass. This is one of the sections, section 3, the one that was coincident with the place where someone was doing an increase of pore pressure. And you can see all these kind of percentage of fines were not invented. They were dragged on by the analysis in CPTU tests. And in the end, the attempt was to have a kind of percentage of fines defined by what I will detail, not detail, we explain immediately after, but in the end we could get this numerical simplification for the model. Again, the panel, the report is very detailed on that. So you can see here one CPTU. If you explore, you have to decide. So the model, to model these materials in each and all position in the ground model recurring to CPTU, and we had 38 points, 38 CPTUs reaching almost 1 kilometer and 37,000 useful data points, which were carefully treated. So the CPTU traces are variable, but they show some consistency in terms of stages of the construction, or even on the position of the spigoting. Wow, what are you saying there? And we can see that in fact, if you look at this, let's say, classification, the first was trying to subdivide in clusters in order to separate the fines to the coarse, meaning the ones that are very permeable and the ones that are not so much permeable. And this can be done with Peter Robertson did a lot, and it's amazing the work that he did on this behavior index, soil behavior index. But the proposal that he did on general materials, I would say usual, non-conventional material, was 2.6 would divide the more permeable to the less permeable, the effective stress analysis in one and drain total stress analysis in the others. But then we had to study that in the silty materials, and we did that already in this liquefact project in the silty sands in Lisbon, great area Lisbon that we studied a lot because of the high susceptibility to earthquake and liquefaction. And then we realized that in this kind of silty materials, marine, marine coming from the inflow, seems that the IC working around 2.85, the one from Peter Robertson and Wright, could be working better dividing these two clusters. And Marcos and all the people that work together, they sat down with this data that you can see here, trying to evaluate if 2.6 was good or 2.7 or even 2.85, which in fact was the one that we used in Lisbon. And it did match very good. In the end, the 2.85 did well. Well, I'm not seeing nothing. I'm just seeing that you are dividing the ones from 2.85. Yeah, but before, that was the analysis that was made, described again in the panel report, that all these data were, let's say, analyzed, reinterpreted, making this subdivision for 2.6, 2.7, 2.85. And you can see here that the blues, the light blues towards the orange, which is here, well, the difference is, okay, this is undrained, this is not, this is drained. Come on, there is a lot still in the, very close, not so different, not so clear. Then let's try 2.7. This is the BQ, by the way, I forgot to say, this is the BQ, which you know it is delta U divided by effective stress, vertical effective stress. And the BQ is a very detailed, a very sensitive parameter to evaluate the permeation of the material. And then if you go to 2.7, you have, well, it gets better. You get this yellow one stands a little bit far away more than the other. And finally, when we get to 2.85, it's mostly clear. Not perfect, cannot be. But anyway, it's really very confiable, reliable. So with the confidence that we got from this, apart from the other work, we split these two areas of fine to coarse, black to red and brown in the lab. But then the dam was by itself zoned in these clusters, looking for this analysis or using this analysis of the BQ. Finally, and complementary, the K values, the ones that we could analyze from the dissipation tests that were available, and they were available, some dissipation tests in this CP2 analysis or tests. Unfortunately, they were not explored any time before. We did that, and then we could also work together with BQ. But not only. Our colleagues from Barcelona and Monforte, one of the researchers that is working very, very, very well on this subject, they developed a method that is limited but still very useful, which is what they call the on-the-fly hydraulic conductivity from piezo cone. This is available. It's a very complex, but not so much, and very useful approach, which is really good to fit, or at least to have a first approach of the kind of permeability that we can have. And then you can see here that the values for fines interpreted by this method, which is here the formulation, are above those of dissipation tests, which means that the method is not precise for every permeable materials, but still for materials below 10-6, it's good for a first attempt and very useful. So, okay, we have the tools. Then obviously we had a lot of permeability in this test that we did in triaxial chambers, cells. We did always the measurement of the K permeability at the end of the consolidation of each and all samples. And also in this set of consolidation, increase stress, confinement stress, effective stress towards the definition of the VS, any of those steps apart from the VS, etc. We also did the definition of the K, the permeability or the hydraulic conductivity. I just put here, and we just put here some of the values that we got from the samples. You can see the samples are the squares here, and you can see the average are here. So the black, the reddish and the brownish, they are somewhere here. So they stand somewhere here in the very drained materials, except these ones which are very fine, which can be close to the slimes. Then you have this increase or decrease in permeability. So they fit it together, which is also very comfortable for our analysis. So these CP2 tests are fantastic for what I said before. But then if you go, again, if you go to state parameter, which is obviously very much explored by this test, then you can see how you can detail, you can get into detail of the condition, the state. So you can see here two of the main CPTU. I say main because this CPTU, this 2935 and this 814 are strictly in the same position in terms of longitudinal, let's say, section of the place where someone was doing, like, it was in fact a borehole with a very high pressure into the borehole that developed excess pore pressures that happened to create the instability, at least for our analysis results. And this happened in this section here, while in that section there seems not to have been created. The problem, yes, indeed, there was a set of boreholes that were coming in different points in this direction, and only after several, the same technique, only here the damage, the collapse was created. And that's why it's important to look at these two as the others, but these two are very clear when you stand for them and you analyze them in terms of interlayering. So the brown one could be red. The brown one was the one that was in the same, mostly in the same point in depth of the borehole. And you can see there is some differences here. Mostly if you look at the, let's say at the lower part of this system here, there's a very, very fine, very much fine with no, a lot, I mean, I have to say that the borehole was at that time somewhere here, 60 something. And you can see all this is very, very much impermeable, very much fine, while the other had a lot of draining layers. So the system was working differently here. Let's look at state parameters. Drag up from different methods. Robertson 2010, plus an old system coming from the only an approach on the critical state position and by a simplification, while Peter Robertson has some indexation, and Main also developed its own method looking for the yield stress ratio, which is very good, is more conservative in general terms, but they stand differently, as you can see here. But still, this area is complicated. Downstream 30 meters seems to be quite unstable. Look at the straight parameters, very high. Look at yield stress ratio, very low. Look at state, less grave, but still. But then you can have here the analysis of the bad one, the one that explained the failure. And you can see that the system here is very complicated. So if you are injecting here high pressures, there is no escape. There is no escape. The parameter is very high. The state parameter is very, very critical. Less in Robertson, evident in Plus, and also in Paul's Main. If you look at the excess pressures that are created during all this process, then there will be all the conditions to create a cluster in materials that will progressively liquefy. So let's go on. So the CPTU is fantastic for this subject. Finally, we did this analysis more thoroughly with the collaboration because Mike Jeffries and they send us the more recent version of their method, and we use that for evaluation of the state parameters. We're using the widget, which is the software that they had to cluster, I mean, to subdivide the drain and non-drain conditions. You can see here that following this analysis, values of B key around 0.02 towards minus 0.02 are drain conditions, while 1.5 are undrained conditions. The other ones will be like you decide. And you can see here that again, Plus considering already the inclination of the critical state line, which is possible, are still much more conservative than the others. And there is some work recent from Andy Fourier, etc., and David Reid. They try to analyze why is this not so conservative in this widget analysis that I will invite you to read. This comes from a very recent work from Andy Fourier and his colleagues. There are some explanations why the widget can be not so conservative. So with the state parameter analyzers, as I told you, with all these CPTU tests, Also, again, the cumulative frequency of the values of the state parameters on plus and on the other widget analysis and whatever. Then you can divide it again, the materials, in terms of more or less higher state parameters, and evaluate the set of clusters, associating them to fines or coarse, lower and higher state parameters. And this is what was implemented in the mesh and on the a lot of analyses that were run in the different sections, different conditions, different hypotheses, to finally, well, I will not detail that. This is part of the result. I would want to emphasize that, again, at that point, at that specific area of the dam, of the reservoir, there was clearly a system behavior, system response, which is here described. Ross Boulanger talks about this, which is very important, how the layering comes to be, and how decisive it is to the drop up of the pore pressure and then downstream to the residual stress, while the others, if you have a system where there is permeation, then you can have higher stability. This is well described in the recent keynote lecture or theme lecture that Ross Boulanger did with Professor Lai from Japan, and they discuss a lot these kind of evaluations that we have to do, looking at how layers develop and how these layers can be particularly sensitive by their interlayering for the triggering of this phenomenon. They demonstrate that sandy soils with silty layers are more prone to flow failure than homogeneous sandy tailings. People know, but not so many. In tailing steep slopes with a laminar structure, it is expected that the localized deformation close to less permeable layer will build up an excess pore pressure, developing a rapid chain of lateral spreading towards downstream. This I had to, let's say, to reproduce here, thanks to Ross, thanks to Professor Lai, because this is said, this is discussed in between the players of tailing dams, but this is really very well expressed in this sentence. Be aware of that. So finally, this was a trigger. I will not go on with this. This is in the panel. I invited you to go there and to look at the details. This is the sliding instantaneously in the numerical analysis, which is incredible. Look at the lateral spreading that is here, pushing down then the mass towards down, towards the bottom. Brittleness index, it is a mainstream, it is. We can now mostly predict the behavior of a specific material, which is unstable, can be unstable by looking towards this index. Why? Because it's strongly related to these ratios of the undrained shear strengths and the effective stressness. The peak one, which is the maximum, there are people that don't like peak, because peak is a hardened material, a dilatant material that goes over the critical state line. It is true. It is true. Maybe it is cemented, or is a residual soil or whatever, or over consolidated in a clay. We are not talking about the same peak. It's a peak inside the stress space border limited by the critical state line. So it's peak, but it's peak inside, is an instability peak behavior. So let's look at the data. So it's the same as liquid. while the critical state will be the residual one, as I showed you before. All these material, the ratios are very sensitive to the brittleness index, which is more or less defined by the ratio between the G naught, or the very high stiffness at the starting of the loading, G naught, versus the resistance, the peak resistance. Can we have that? Yes, in the lab. But can we have that in the field? Yes, we can. If you do CPTU analysis, you can have that. If you can do other tests, like pressure meters or even SDMT, not so thoroughly analyzed and interpreted as the CPTU. So we will rely on that. And by the way, if we have that, do you have any idea if the values of the residual stress in drain stress is valuable, the one that we have from the CPTU? Yeah, well, people did a lot. Peter Robertson has a lot of data that he treated. More recently, others did, like Olson, etc., did reapproaches of some of these back analysis of failures, and they have been doing some amelioration, the improvements of the values. You know that it is expressions between the SU residual towards the CPT, normalized. And well, there is a very recent work from Professor Lai from Japan, again in this keynote lecture in Sydney. These results are presented, and look, it's really important, this work, because it was a very thorough and very complete analysis of the set of places where the system and they did the back analysis of each and every points that they had enough data, geometry and data to analyze. And all these balls here are the retrofitting of these. You remember that this huge, immense mass of mud coming into the valley from these outside crops and going down and sliding. So they did analysis in different points in order to evaluate the shear strengths in flowing post liquefaction, and evaluated the sigma prime on each and every of these areas, and they got this relation between, well, you know, Japanese like SPT, not so much CPT, but at least what is here important is that we have a border lower limit, and we cannot go to the upper limits. So if you want to design, you should look at these values. They may be as low as 0.03. So be conservative, which is not the same materials that we have in the tailings, but we should always be aware that they can be as low as that. The lecture also will include some analysis on other tests in other areas of the dam, which site 3 is very rich, because site 3 was collected, unfortunately, arrived in our lab after we had to finish the panel, the report. But we were allowed to continue to work. Val is aware of that. In fact, one of these papers will come soon. It's already finished in a journal, which I cannot identify. And this is the data that we developed more thoroughly. In black material is the one that is really dominated the area that failed. And you can see here some of the results. I will not detail this because it will appear in more detailing in these papers. But what I want to tell you is that we did define clearly that the instability line in this case are mostly independent in terms of if you look at the K naught equal to 0.5, 0.7, or 0.1, as I already referred. The critical state line mostly is unique, but these are the dilated materials just for us to understand and to integrate in the numerical analysis. And this is a much net and clear image of that results, of those results. But then I start here to plot the ratio between the undrained shear strengths in the peak, normalized by the effective vertical stress in K naught equal to 0.5, 0.7, and 1. And there is some influence. By the way, there is a paper that was published on the Brumadinho data, some recent in a conference, but it's not so complete. So we have to be aware of that, but we don't usually work with P prime. No, usually there is no. We usually do sigma prime V naught. Yes, we do. So we have to be aware of that. If we go to a limited analysis, a limit equilibrium analysis, you should be aware of that. When you take the sigma prime V0, you have to look at where I'm standing in terms of K naught in order to use that value. And then I decided to, well, Marcos did also something similar in his conferences, but this is more complete here. And you can see here the set of data that we analyzed in this plotting. Site 3 is here, but also the others that were already before in the report. Do you remember the black, the red, and the brown? And then the open squares is the new material on site 3. And you can see here the dependence is obvious. You can see here 0.42 for K naught equal to 0.5, 0.28, 0.19. So 0.19, you have the SU peak is all data is somewhere here. These are the data of that K naught 0.5. If you look at the 0.7, the data is all here. And if you look at the 0.5, which most of the tests were done in this condition, all the data is here. A lot of them are mostly zero in terms of residual because it dropped down and we could not drag the connection with the critical state line in the stress pass. But then if you look at the trend, you see like, wow, the blackish one is terrible. It's terrible. So it seems to have a very low condition, very low. Indeed it has. So I try to map here in the first approach, how can we go towards like a trend? And look, wow, you can have even less than the values that Professor Lai defended around 0.08. Okay. So eventually, if I don't have any more, I will go for 0.08. And these are very low values. Finally, do you remember that we talked some time ago on the stress passes and the influence of anisotropic behavior, inherent and induced? When we look at the place where something was done in order to increase here the pore pressure, and with that increase systematic and continuous increase of pore pressure in time during the enough time to create an excess pore pressure in like a cluster here, when it triggers some kind of liquefaction, then you have a complete evolution of that increase of pore pressure, increasing the lateral stress towards downstream, while it immediately it immediately deducts the pressure down. So you can see the images of the stress pass tests from the K-naught consolidation are essential for evaluation of these actions. And what I want to emphasize here is that here you can have a much higher undrained peak strength than here. And that I was showing you when I was showing this compression test. No, here is only compression stress. If you want to be strict on the positioning on your finite element code or different finite code of your position of your points, you have to put them in the K-naught position that you think and rely on. And then I will talk about the extension tests. If you look at the extension tests, if they are here, sorry, this is too heavy. I told you that the amount of the increasing pressure is so high that the values of the undrained shear strength is mostly equal to the residual one. It's very low. So look, these are the values of the highest deviator stress when you increase the lateral pressure in the stress pass. Okay, it's axisymmetric, not plane. Plane will be a little bit higher, the value of the ratio, but it's still very low. Here is 0.06 again of all these 4 tests that we did here. If you get a plane strain, which I don't get here, I don't have, there are people that have like Panakovsky and Professor Yu, etc. You will get very low values. So anisotropy, we can have inherent anisotropy, we can have induced anisotropy. By the way, the colleagues from the UWA, David Rader and his colleagues, and Andy Fourier is in this team, of course, they tried to analyze how this can be important to look at the K-naught values and the inversion and the rotation of the stress, so the alpha value, when you look at a specific tailing pond. And look what we have here. This is their analysis in finite element code. In this paper, very interesting paper that you should look for. And look, you can have these K-naught values just emulated by numerical analysis, you know, around 0.75 here, while you can have here and somewhere here very low values. While if you look at the value of the state parameter that you get from this side here and that side there, it seems to be improving, let's say less positive, but still positive, which is like you have still the instability present, but the K-naught is much closer to instability line. Wow, that's the issue. That's the issue. Your stress straight at repos is very close to the instability. For instance, if you increase the pore pressure, it goes very fast to the instability line. So the instabilization is fast and sudden. And for not so much action, you get the problem. Do you need to determine the K-naught values in your structure? Just do it. How? You can do a pressure meter, a self-boring pressure meter. Quite complicated. We all agree. Difficult to perform that in the ponds. You can do in the piles, the big piles, you know, these dry stack piles, etc. Okay, it's very expensive. There are so many in the world. But then you can do PMT tests with a small rig, a hogger, and then you do the test. You don't have the K-naught, but you have an idea of the value, which is not K-naught because you have a pre-bore, then you have to put the pressure meter there. But then you can at least relate the different values from the crest inside the deposit and to see how it changes. Pressure emitter. But then the simplest one is the DMT. Okay, it's an approach. It's well calibrated already. So I'm very fan of this. If you want to have an idea of the K0, an idea towards the KD, which was very much developed, very well developed and interpreted and correlated by late Professor Silvano Marchetti. So do it, because it's valuable to know where we stand for K0s. Finally, if you use the seismic model, you can have the VS and you can have the VP. There is no justification of not using what is available to do better. So finally, I'm discussing here some of the numerical simulations that we did on some of these tailing dams or tailings materials and we are doing in Minas Gerais. And I just want to show you some simulations that we did in a specific material, which I will not identify, in tailings, of course, very similar to the ones in B1. And we calibrated this in North Sand. We are used to do that. Traditionally, we use this approach from Mike Jeffries and Don Shuttle's spreadsheet. We did also some Plaxis element tests using the parameters that we calibrated from all these tests that I showed you before. But the ones that we had, compression, we have extension, but we had to calibrate it in compression because it's what we do usually. And finally, look at the results. Oh, come on. So you have here very good representation with your parameters. But if you do one of these tests in 300 kilopascal with K0, wow. But then if you go to the pre-prime, you have, wow, it's not good. Not good. Why is that so? Because we calibrate this with the isotropic tests. Oh, so it's usually done by, yes, usually we calibrate by isotropic tests. Very good isotropic tests to have the critical state line and the latency or whatever you can imagine. All the data that is necessary to identify these North Sand models, and it doesn't work for different pressures. So should we be aware of that? We have to be aware of that. This is an MSc thesis that was finished this week and will be available. And you can see here that if you look at the Flux is a problem. No, it's not. It's a very good frame. But we did that also in FLAC. Because, I mean, there are people that say, no, FLAC is good because it gets all this explicit analysis, etc. We did also with the FLAC, and the problem still stands. So we have a different behavior when we simulate and towards the test. So we have to work very much on this. The models will have to incorporate anisotropy. And in this case, is the K0 that is demanding for a kind of isotropic versus anisotropic behavior, let's say. It almost like a fabric induced, so it becomes inherent in terms of it's an intrinsic value of the condition of the stress at repose. While if you look at the extension stress passes, I will not show some of the most precious data, which is in loose sands, in loose tailings, sorry, but at least I'm showing you here that if you look at the stress passing extension in dense soils, in these dense materials, so they are not going to be instabilized, but they will contract because we are increasing the lateral pressure. in undrained conditions, in the lab test, you have all these increase in pore pressure. So you can see this would be the drain condition, drain condition, drain conditions. But in the lab, you have all this increase in pore pressure. While in North Sand, in flak, you have this and this and this. So really different. So the anisotropy is not working well here. And you say, well, that's a problem of the critical state line. It is not. Because if we do the emulation of the drain test, everything stands well in phase with the critical state line with the same angle of shearing resistance. So we have a problem. So we have to solve that. So the next future in terms of modeling will be definitely to invest in the anisotropic approach of the modeling of these materials. And this is just an image of the K naught equal to 0.05, that 0.5 that we use in B1 in terms of modeling. So we have some conclusions here. I have just in between brackets that people from UPC are now working with CPTU, and in CPT 22, there is an excellent resume of these last proposals. This one was in Computers and Geotechniques, the journal, coming from Luis Monfort and all these colleagues that I told you that lead this group in Barcelona. And they have a very net interpretation of the possibility of working with pore pressure or the cone base QC, QT of the CPTU, and from the analysis of one versus the other, they can go towards the definition of a value that is close to the peak and a value that is close to the residual and drain shear strength. So look at this, it's improving. It's a very interesting analysis, and it's really very much dependent again on the brittleness index, which is in fact the key issue for us to know if we can expect to have higher, less high, or even null fragility. So considerations. Well, you can read this. I'm sorry, it's too long already, but this is the main issues. We have to be aware that these are tricky materials. We have problems of brittleness. We have problems of using limited state equilibrium analysis. If we don't care about this evolution from peak to residual, we have all these possibilities to go towards more complex but available stress-strain couple analysis in Plaxis, Flaccio, or whatever. And so let's keep on working because we have a lot to do. Some acknowledgements, please do stand for a moment. Very much recognized to Vale, allowed us to do all this. MPF tried to go to the different approaches to get the reasons why this dam collapsed with so many damages. Special emphasis to Professor Marcos Arroyo and Professor António James, which I have the pleasure to be a very good friend. They did an incredible work. People from Sebastião Oliveira from MPF and Leonardo Mesquita and all these people here that work together with me, fantastic guys. And of course, Professor Antonio Mendoza, which was very, very, very dedicated to the second and third campaigns. I could not go there because I was in confinement in Portugal. I could not go back to Brazil. And finally, my people, my colleagues, António Fonseca, Cristiana Fonseca, a lot of Fonsecas, Daniela Coelho, Diana Cordeiro, Davide Besançon, Fausto Molina, PhD student now in the NGI, Daniela, technical director of the laboratory that I directed, and finally Antonio was a researcher here, and Cristiana is assistant professor, invited assistant professor here. So, God bless. This is what we have to do. Failure is not an option. And obrigado in Portuguese, grazie in Italian, because it was in first time presented in Bologna. Thank you. And thank you, Jim. God bless, because you did inspire so many people and myself. This was presented in 10th June, which is the day of the Portuguese nation and Lusophony. And please, lab is important. We will have the next symposium of the TC 101 in Porto next year in September. And it will be a lot about this and other things. Thank you so much for your attention. I look forward to put this immediately or as soon as possible in our website. It will be free available in YouTube. So I just want to say goodbye and God bless. Thank you.